Okay, so before we get started, quick show of hands. How many of you actually have applications that are using adaptive hashes? Does anybody know what adaptive hashing is? Okay, so one person knows. All right, so we're going to go into the history a little bit about password storage and how we got into the area of adaptive hashes, why it's important for us to use adaptive hashes, and then we'll get into the problem of denial of service when you are using adaptive hashes. So we're going to start off by just talking about password storage, what the problem is, in the context of when you're storing passwords for your application's users. In some cases, you're storing passwords in your application to authenticate to other applications, and in that case, you can't use hashing, but that's not something we're going to address today. We're going to talk about some solutions to this problem. We're going to then talk about some client-side computational capabilities and compare them to our server-side computational capabilities, as well as our capabilities of our attackers. The reason for that is, when we start talking about DoS attacks, a lot of the stuff we're going to read out there on the internet really talks about pushing the work to the client side. And we're going to talk about how just doing that across the board blindly doesn't work. And so, what is the password storage problem? So for a typical web application, we've got our application server, we've got our database server, maybe we've got some backups of our database, and we've got some browsers. We've got people from the outside connecting into our application, and how do our passwords typically get stolen? And I'm sure you've heard of many, many instances of password databases getting compromised, and there's the external attackers that we're worried about, who might be able to conduct attacks like SQL injection to get to our passwords, or maybe even get to our backup tapes. So, for example, getting stuff from a storage shed. We also have to worry about compromised servers and malicious admins. There have been instances in the past of malicious people, malicious employees who get disgruntled, getting a dump of your database and selling that to somebody. So another thing we have to worry about. At the end of the day, though, this is what we have. Regardless of the type of attacker, we've got a dump of our users table from the database. Usernames and passwords stored in whatever format that we're storing them in. So how do we protect ourselves when this happens? Well, we need to prevent, for the most part, offline attacks against whatever the attacker gets access to. And we have to keep in mind that the credential store, the passwords, are only going to be valid for a limited amount of time. Eventually, hopefully, in all reasonable organizations that have some reasonable monitoring controls in place, the attack will get caught in a few months, maybe. Longer than it should take, but it eventually does get caught, and users might be forced to change their credentials. So we really have to, the attacker has to operate pretty quickly. So that password store is not going to be valid for the next 5, 10, 15 years. One quick note, client-side attacks before or after that database gets compromised are really out of scope for us. That's not something we can address using password storage mechanisms. So, back in the day, this was maybe a long time ago. We'll see, it actually wasn't. But starting in the 1960s with the very first versions of Unix, how did they used to store passwords? In the clear. So what's the problem with that?
Assuming a lot of trust.
Assuming a lot of trust, right. So there's essentially no protection once the password store gets compromised. And even back in the 1960s, we kind of learned our lesson. So there's a story about two people who worked over at Bell Labs back in the day. One admin was editing the etc password file, and the other one was editing etc motd. Anybody know what motd is? Message of the day, right. So due to a glitch in the system, when the one admin tried to save the password file, it actually overwrote the message of the day file. What do you think happened after that? Every single user's password would get exposed to anybody who logged into the system after that. So I'd like to say that we fixed that problem, but even April 2014, there was an application that was storing users' passwords just in the clear. An attacker with SQL injection was able to get them all out. So even today, many, many applications are doing this. And even in the absence of any application layer vulnerabilities, we have to think about, well, should our database administrator in our organization really be able to read your CEO's password and the password of every other person in the organization? So, how do we solve this problem? And we have to talk about the history of solution so that we kind of understand the context behind adaptive hashing. So this was one of the first solutions, and unfortunately people still use it to this day. We just store, instead of the password, a cryptographic hash of the password. So in this particular example, instead of storing the two passwords that I showed you, I just have SHA-1 hashes of those passwords. Now, the reason why we do this is because of the one-way property of hash functions. So given a password, we can compute the hash, but given a hash, we can't compute the password. So that's a desirable property. So now if somebody gets access to our password database, they can't just compute our passwords from the hashes. However, where we get in trouble is the ease of computation property. Hash functions are designed to be really fast and efficient because they're really designed to hash large pieces of data. You want to be able to hash a 5 gigabyte file in just a matter of seconds. So they're meant to be really, really fast. That's what gets us into trouble. So there's 3 different types of attacks that we're going to talk about here. There's pre-computed hash tables, brute force attacks, and rainbow tables. So these are, of course, attacks against if you're just storing cryptographic hashes of your passwords. So what's pre-computed hash tables? It's really kind of the naive approach of guessing all possible passwords and storing the password and their hashes. Lots of pre-computation, lots of storage required. So for SHA-1 hashes and 8-character alphanumeric passwords, if you wanted to have a hash table of every single one of those passwords, that would be greater than 6 petabytes of storage. So really kind of unreasonable. However, if we actually did that, once we got a database of SHA-1 hashes, we could recover them pretty much instantly. All we'd have to do is a table lookup. We've already done all the computation work. Brute force is the other end of the spectrum, where we don't do any pre-computation, we don't store anything at all. And when we get the actual password stable, we start reversing all the hashes. Now in the worst possible scenario, again, 8-character alphanumeric passwords, SHA-1 hashes, just on my laptop CPU, it would take me about 2.4 years to recover all those passwords. So that's getting a little bit unreasonable. Remember, our table is only valid probably for a few months. However, if I wanted to invest in a $1,000 GPU, I can cut that time down to about 10 hours. Now that's a lot more reasonable. Now think about that. If your password policy, and many organizations had this, allows for 6, 7, 8-character passwords, somebody with just a $1,000 GPU, if you're storing passwords just as SHA-1 hashes, can reverse them all in just a matter of hours. And somebody actually built a GPU cluster back in 2012 that could actually do this job in less than an hour. So, pretty scary. Now, rainbow tables essentially achieve a compromise between the two approaches, where in this particular case, for 8-character alphanumeric passwords, SHA-1 hashes, you would need about 135 gigabytes of storage and some pre-computation. It allows for almost instant password recovery without using GPUs. So now using just my laptop CPU and rainbow tables, I could reverse the passwords pretty quickly. In terms of algorithms, back in the 1970s, there was a DoS-based hash function that Unix used. Essentially what it did was you would have up to an 8-character password. It would encrypt a constant with that password. It would do the encryption 25 times, and it would store that value. Anybody know? Well, so DoS is an encryption algorithm, right? So normally we would encrypt the password with a cryptographic key. Anybody know why they chose to encrypt a constant with the password and actually did the encryption 25 times? Well, if you think about it, if you are encrypting passwords with a key. What happens if that key gets compromised? Now, that person can decrypt all your passwords. If you're using the password as the key, there is no key to protect. It essentially turns it into sort of a one-way type of function, hash type of function, where you have to have the password. You can't just go backwards. And the encryption was performed 25 times, essentially to slow it down, because people realized DES was too fast. And we'll get back to that theme when we start talking about adaptive hashes. And of course, we've got things like SHA-1, SHA-2, and so forth these days. SHA-2, it's a newer algorithm, no more secure in terms of the types of attacks we're talking about. So the problem with cryptographic hashes, unsalted, is that, again, depending on your password policy, most hashes might be reversible using rainbow tables and brute force attacks, like the LinkedIn incident back in June 2012, right? So in that incident, when attackers got the SHA-1 hashes, 60% of them were reversed in just a matter of a couple of days. So we get to the next approach, salted cryptographic hashes. So before GPU attacks, FPGA attacks, ASIC attacks became popular, the main things we were worried about were rainbow table attacks and low entropy passwords. So the solution we came up with was, well, let's add a unique cryptographically random value that gets stored in the clear to the password before we hash it. And that value we can store in the clear along with the password. So our password store looks something like this. We have the salt, and then we have the hash. Now, how does this protect us? Well, if we start thinking about brute force attacks now, and let's say we have a database of 10 million passwords that are just salted hashes. Assuming that we're using long random salts, the time to reverse all of them just becomes infeasible now, because now you have to crack every single hash separately. So we can't now reverse all the hashes in a reasonable amount of time, but we don't need to. The attacker can just target individual passwords at a time, or the attacker can just try weak passwords across all the accounts. There's many different ways around it, but typically the attacker might just target some privileged or high-value accounts and just get those particular passwords. And we can still do that, as long as those passwords are easy to guess. Now, rainbow tables, we sometimes hear about rainbow tables for salted hashes. There's really no advantage in this case. It's feasible if the attacker is able to get the salt value for a bunch of high-privileged, high-value targets in advance. So you can compute a rainbow table, so as soon as you get the actual password hash for that system, you can crack it almost instantly. But in general, you can just do a brute force attack pretty fast. So there's no real advantage to rainbow table attacks now. In terms of algorithms, we've got the exact same thing as before. We just add a salt to our hash. Now, the problems with this approach is that users tend to choose very weak passwords. So according to a 2007 study that Microsoft did, 20% of users have passwords with less than or equal to 20 bits of entropy. That is very, very small. That's very easy to brute force. And then 55% of users out there have passwords with 30 bits of entropy. So if we just want to target these users, how long would it take if we're just using salted cryptographic hashes? Not very long. So 20% of your users' passwords can be cracked in just a matter of 30 minutes with a $1,000 GPU. 55% of your users' passwords, maybe 20 days. And depending on how much hardware you have access to, it can be a lot faster. So, salted cryptographic hashes, the main concern we have now is weak passwords. And there's not much we can do about it. We can enforce password policies, but at the end of the day, people will still want to choose easy to remember passwords. Well, one solution to that is to add a key, sometimes also called a pepper, to our salted hashes. So our approach before was to have a salt and a hash of the password and the salt. Well, now we add a key. And now what that does, as long as the key is protected and the key doesn't get compromised along with our table of usernames and passwords, we don't have to worry about brute force attacks, rainbow table attacks, and so forth, as long as that key is unknown. And this is the only approach that actually offers a fair bit of protection against a malicious database administrator or a compromised database server as well, assuming your key is being managed on the app server. So you get some advantages there. However, you get no added protection if that key gets compromised. So you're back to essentially salted cryptographic hashes if that key is compromised. How we actually do this? There's a couple of approaches. You could just simply concatenate the key into the hash, or you could use a message authentication code. Doesn't really matter. It's really the same idea. But there's problems with this. We've added the complexity of key management. And now this is not a simple problem to solve, right? And the problem is actually really difficult here because, well, whenever you want to change the key, which you should be doing every 1 to 2 years, how do you rehash all the passwords? Remember, you can't get the password back once you've hashed it. So you have to wait until the user logs in. You have to verify the salted keyed hash using the old key, and then you have to store the new hash password. Possible workaround, encrypted salted hashes. So you have a salted hash and then you encrypt it. That way you can just decrypt it because the outer layer is what uses the key. However, combining crypto primitives like that is non-trivial, and if you make a mistake, that might actually make you vulnerable to various types of attacks. Now that brings us to adaptive hashes, which is really what the main point of today is. It's really a different solution to brute force attacks that doesn't add the complexity of key management. So it's an alternate solution to the keyed salted hashes. What it does is it removes the ease of computation property of hash functions. So now hash functions are much more difficult to compute, and it's equally secure against all potential threat agents, or potentially equally insecure. So what does this do to our attacks? Brute force attacks. Well, we can make these as slow as we want. So if we want the time to compute a particular hash to be 1 second, 2 seconds, whatever, we can make it so by just changing the adaptive hash parameters. So we're slowing down the attacker. However, remember, every time you have to authenticate a user, you have to compute these hashes yourself. So you're creating load for your server. Now, okay, well, so we have a little bit of a balancing act, and we also have to remember that an attacker can build some specialized hardware that can compute these typically about 2,000 to 3,000 times faster than any high-end server. So the attacker is always going to have a bit of a speed advantage. In terms of rainbow tables, again, just like with salted hashes, if you happen to know the salt for your targets in advance, you can compute these in advance. And in this particular case, you might actually get a significant advantage over brute force because you're doing all the slow hashing work before the table gets compromised. And once the password table is compromised, then it's much, much faster. So in this case, the attacker might actually want to build some rainbow tables for some high-value accounts, for example, for your admin account, if he can get the salt in advance. In terms of algorithms, you might have heard of some of these, PBKDF2, bcrypt, and scrypt. In terms of complexity, it's increasing as you go down the list here. PBKDF2, it's sort of one of the first adaptive hashing functions. You can make it arbitrarily slow. However, just due to the nature of the algorithms, you can parallelize it pretty quickly using GPUs. bcrypt makes it a little bit harder. scrypt makes it even harder. But even with scrypt, there are ASIC-based implementations available that will work for some scrypt parameters that'll do hashing about 3,000 times faster than any of your servers could. So we still have to keep that in mind. Even if we are using adaptive hashes, if your attacker is really, really committed to and really motivated to try to attack you, they will still be able to. In this case, they have to spend $7,000, but oh well. If your attacker is motivated enough, they will do that. So what are the problems with adaptive hashes then? They require a lot of computation from your servers. So the more we scale up the adaptive hashing parameters, the more work our server has to do to log in any user. Now, there's a few different approaches we can use in terms of when we compute these hashes. So typically, your users are going to be supplying a username and password. You can check the username and then say, well, if the username is valid, then I'll compute the adaptive hash. to see if that password is correct. Or maybe I compute the adaptive hash every single time. What's the problem with the first approach, where I only compute it if that username is valid? Just through an authentication attempt, the attacker will know whether a given username is valid or not, because if that particular username is valid, then the response will be slower. Because your server is computing the adaptive hash, that's a slow operation. If we compute the hash every single time, well, you're creating an easy denial of service opportunity for your attacker. All the attacker has to do is just fire away tons of username and password requests at your server, and your server is just going to chug away trying to compute those hashes, and it can't service any actual requests. Right? So we also have to think about, well, our valid usernames might get locked out, so maybe that somewhat mitigates the attack. But do we verify these hashes when these user accounts get locked out? If we don't, then that's another username enumeration attack. If we do, well, then you also have to track, well, if you do actually, if you stop verifying the hashes for accounts when they get locked out, then you have to emulate that behavior for invalid accounts as well. Because otherwise, I can figure out by the fact whether a given username is getting locked out or not, I can figure out if that's a valid username or not. Now, in username enumeration, not a huge problem, but still it's something we do have to worry about in some cases. So let's talk about client-side computational capabilities. And now this is important because if you ever just do a Google search about how to prevent denial of service attacks when you're using adaptive hashes, a lot of the approaches talk about, well, we could just make the client side do it. Why don't we just have the browser compute the hash? Or many variations of that. Well, this is really important to consider. So here are some numbers for a SHA-1 based adaptive hash. So these numbers aren't going to be true for bcrypt and scrypt, for example. There's not going to be that big of a difference. However, if we take a look at desktop browsers, right? If we want to create a 1 second delay, if we want a typical laptop computer to require 1 second of computation to submit adaptive hash to our server, what does that mean? It means about a 15-second delay for a relatively modern mobile phone. If you're supporting mobile users, that could be a problem. However, how much are you slowing down the attacker really? If the attacker has some specialized hardware, he can compute up to 540,000 of these every second. So it's not a level playing field, right? So if we say, during the authentication attempt, let's say we make the browser do all the work. It's going to slow down your users, but it's really not going to slow down the attacker very much. So we can't just blindly do that. So how do we prevent the denial of service attacks when we're using adaptive hashes? How do we make sure that an attacker can't just bring our server down? Well, we're going to take a look at 5 different approaches. The first approach is sort of the more straightforward approach. We just move all the hashing to the client side. So you go to a login page for your application, you supply a username, and the application sends back a salt for that user, as well as some adaptive hash parameters, how many times to iterate the hash and so forth. The browser does the computation, submits the hash to the server, and the server verifies if the hash equals the stored hash value. Anybody see any problems with that? Other than the fact that, well, you can't have the hash parameters very high. You can't have them high enough to actually slow down attackers. Does anybody see any problems with this? There's information leakage. You're sending the salt to the browser. So remember some of the pre-computation attacks we talked about that might use the salt for known user accounts.
And you verify that the user account is valid, the username is valid.
If the username is valid, yep, you can try to hide that fact by just always returning something. But yeah, at the end of the day, you're leaking information about whether the username is valid, and you're leaking salts. But there's a much, much bigger problem here. Remember what we're trying to protect against. We're trying to protect against a scenario where your password database gets compromised. In this particular protocol, once your password data is compromised, those values that are stored in the password column are the values that the browser needs to send to the server. So there's no reversing required, right? So if an attacker gets a copy of your passwords table, he can just send those values to the server and authenticate as those users. Those hashes are the passwords. So not a good approach to use. And also, remember that attackers' computational abilities are much, much greater than your users. So it's going to force you to use insecure adaptive hashing parameters that are not going to slow the attacker down at all. Let's take a look at another approach. So this approach involves using two hashes. So we're trying to solve that problem of, well, if the password table gets compromised, those values are the passwords. So what we do is we do adaptive hashing on the browser side as before, but what we store on the server side is just a traditional cryptographic hash of what the browser sends. So we have essentially two layers of hashing. We have a slow hash that the browser has to compute, and then the fast hash that the server has to compute. So now the server doesn't have to do a whole lot of work. And the values that are stored there, well, they can't be used to just log into the server. Anybody see any problems with this approach?
Well, we're using the fast hash on the server side, so that's all the attacker needs to do.
Technically, yeah, the attacker only needs to break that. Now, one potentially good thing about this approach is that you actually have to start from a password to be able to get the values that are stored on the server, right? So you have to, if you're building a hash table, you have to compute the slow hashes as well as the fast hashes. So it does maybe slow you down, but the attackers can get the user salts in advance, right? So I can do the slow hash computation offline before I get access to the passwords table. So if I build hash tables offline, when I get access to the passwords table, I just have to compute the fast hashes. So now the security kind of falls back down to just salted cryptographic hashes with a whole bunch of pre-computation required. So again, not the best approach because it doesn't really protect us against the types of attacks we're concerned about. And of course, just like with the previous approach, we can't scale up the adaptive hash parameters quite enough. Now, what if we just use a simpler approach? Instead of offloading the computation to the client side, we just say, well, you can't submit more than X number of requests per second, per minute, whatever, from a given IP address. Does that protect us? So we just say, when we get a username and password, we get an authentication request from the browser. We say, well, does the number of authentication attempts from that IP exceed our limit? If so, then throw out the request, return an error, otherwise verify the password. Why doesn't that work?
You have a botnet.
Exactly.
DoS regardless.
Exactly. So, and you don't need a huge botnet. I know that I'm fudging some of the numbers here, but let's just go with it for now. So let's assume you allow one request from an IP address every 5 seconds, which is actually a pretty slow rate. Let's say our server takes 100 milliseconds to verify the password because, well, it's a slow operation. And if the server has 8 cores, an attacker with access to 400 IPs can cause a denial of service. I know I'm fudging numbers here, but that's fine. Eventual blacklisting of IPs, so if you see a whole bunch of requests coming in from IPs at a sustained rate, you could just blacklist those. But again, if the attacker has access to thousands of IPs, they'll just try 400 at a time. When they get blacklisted, he'll just move on to the next 400. So it doesn't really solve the problem. However, it's something good that we should be doing regardless, because it will stop certain types of attacks. What about using a proof of work scheme? Does anybody know what proof of work is? So let's take a look at the actual idea behind proof of work. So this is sort of a straightforward proof of work scheme where the server says to the client, here's a random value x, give me another value y such that the SHA-1 hash of x concatenated with y starts with a certain number of zeros. And you can make that as many zeros as you want. And the more zeros you add, the more work the browser has to do to find a value y. So the client has to try random y's until it gets the required hash. That's typically going to require about 2 to the n computations, where n is the number of zeros that you want up front in the SHA-1 hash. Then the client sends the value y to the server. The server verifies that that value starts. The server just generates one hash, x concatenated with y, makes sure that it starts with n zeros. So now the client has to do a lot of work to find that value y, on average. The server has to just verify one hash. So if we were to use proof of work, how would that work? We go to a login page, the server will send some proof of work parameters, the number of zeros, the algorithm to use, and so forth. The browser starts computing it, maybe right away. The user puts in their username and password, submits them. As soon as the proof of work value is ready, the username, password, and proof of work get submitted. The server verifies that the proof of work is valid, and then verifies the password. If that proof of work is valid, if it's not valid, then it just throws it out. So now, what is this really doing? Well, this allows us to use secure parameters for adaptive hashing on the back end that are actually relatively slow. We don't have to rely on the client-side computational abilities. So we're separating our adaptive hash parameters from another control that's slowing down the client side. Now, does this work?
What about doing this on a mobile device?
Exactly, right? We have the same problem as before, right? Now, it's something that we probably should do. Now, does it work in every scenario? No. It will help in some cases. So the problem is, again, that attackers' computational abilities are much, much greater than your users, who might be on mobile devices, who might be on desktop computers, just running this in JavaScript. Now, so we can't just scale up the proof of work parameters. So, well, we would be able to scale proof of work parameters sort of independently of our adaptive hash parameters. So when we're under attack, we start scaling it up to slow down our clients, so our server doesn't get impacted. But when we start scaling up those parameters, it's going to impact our users a lot more than the attackers. So if we have an attacker with a GPU cluster that we're worried about, and we want to create a 1-second delay for every single password that the attacker submits, that's going to mean a 6.5-day delay for a typical desktop user, and probably a couple of months for a mobile device user. I don't think anybody's going to wait that long to log in. So alternately, we can start scaling up the parameters by the client's IP address. So that's a little bit better now. Now, the advantage of the proof of work scheme is you can actually do things like that. You can scale up parameters by IP. You can use all sorts of heuristics, so you're not causing pain for everybody, just the machines that you think are attacking you. Now, what happens if the user happens to be behind the same NAT device as the attacker? So now your legitimate user's IP address is the same as the attacker's IP address as far as your server is concerned. What do you do about that? Sorry?
Well, then the users are out of luck.
Users might be out of luck, so you do, but the attacker can technically, well, we're going to assume in certain attack models, the attacker might be able to manipulate that.
Yeah,
So,
but like you're talking about not like cutting out the users. So users, but the
yep.
user
It depends on where the attacker is. If the attacker has access to the NAT device, then no. But if the attacker doesn't, then maybe that might work. But yeah, ultimately, we can use approaches like that, or we might just say, well, that's only going to impact a small number of users, so maybe that's okay for a short period of time. Or another approach we can say is, if our users' email addresses or phone numbers are on file, what we can do is, for legitimate users, when we're under attack, and only when we're under attack, we can say, well, you can click here to get a token sent to your email address, and instead of the proof of work, you can submit that token along with your request, and it allows you to bypass proof of work and just log in. Now, we have to be careful about how many of these tokens we issue per user, per day, per hour, so forth, to make sure we don't cause a denial of service attack. But The good thing about the proof of work scheme is it allows you to do things like this. So we're not just saying we have to use insecure adaptive hash parameters. We just have a separate control, and we can use it as we see fit. Now, the last approach we're going to talk about is prioritizing user logins from known IPs. So for a lot of applications, the majority of our users are going to log in from IP addresses that they've logged in from before. Most users aren't going to log in from a completely different IP every single time. And we can use that to help us in some cases. So as before, when the user submits a username and password, we have to figure out whether we want to verify the password or not, because that's a computationally intensive operation. So if that user has previously authenticated from that IP address, then we just go ahead and verify the password. If the user hasn't authenticated from that IP address before, then we just add that login request to a queue. We add the username and password, maybe some kind of timeout value, and the IP address that the user is logging in from. We just add that to a queue. And if we're getting too many requests in the queue, some of those requests will just time out, and we just return errors to the browser. So something we have to be aware of if we're using this approach, even for username IP address combinations that are sort of whitelisted, the user has logged in from them before. If you're getting too many authentication requests from that IP for that user, we still have to start adding them to the queue because we might be under attack. Now, we also have to make sure we only dedicated a limited number of computational resources to processing that queue. We don't want to just say, well, we've got 50,000 requests in the queue. Let's just dedicate all of our service resources to processing it. That doesn't solve the problem. So we might say, well, we're going to dedicate only 2 server threads to processing that queue. Whatever login request we don't get to, well, too bad. But our legitimate users who are logging in from known IPs still can. Now, this approach will only work if the attacker can't just create 100,000 accounts for himself and log in from various IPs, and now he's got 100,000 accounts and a bunch of IP addresses that he can launch this attack from. So this type of approach might work well for online banking, but probably not for something like free webmail, for obvious reasons. Now, the attacker in this particular case can still cause a denial of service for users that are trying to log in from new IPs, and we can use the same sort of approach as before. We can issue tokens at a limited rate to allow users to bypass this. So, at the end of the day, we probably have to combine several approaches because none of these approaches is perfect. We want to make sure an attacker can't cause a denial of service attack. So what do? Well, one thing you should never do is just offload hash computation to the client side. It's going to force you to use insecure adaptive hash parameters that are not going to slow down the attacker. There's a huge, huge gap between your typical users' resources and their computational abilities and an attacker's. So at the very least, we want to rate limit our login requests by IP address. So maybe 1 login request per 5 seconds from an IP address. That will protect against a handful of malicious clients, which is good. It's not perfect. Require clients to submit a proof of work and scale it up by IP address, and we want to scale it up exponentially to really slow the attacker down. It will protect against some smaller botnets. Prioritize user logins from known IPs. That's the last approach we talked about, which will potentially protect against larger botnets, but only if the attacker can't just create a large number of user accounts himself. And as we talked about, allow legitimate users to request 2 or 3 tokens per day to bypass proof of work, to bypass these prioritized logins when you're under attack. Again, is this going to protect us against every possible scenario? Probably not, but it's going to be much better than just not doing anything. Yes?
Why don't you have captcha on the list? Is it because you are afraid of mechanical trucks? My impression is that like, if mechanical truck is used, it's going to die to compute like a real attacker.
So why not use captchas? So I did actually think about using captchas. A couple of reasons why I didn't talk about that approach. One is that it's really annoying for users, right? So.
I mean, not like in the very beginning. But
yeah, but when you're under attack.
But when you have too many requests,
yes.
you can turn it off.
Yes.
I've seen it like on money servers and
Yes. The problem with that is our AI algorithms for actually solving CAPTCHAs automatically have gotten really, really good, even better than people. I mean, there's algorithms out there that can solve a lot of CAPTCHAs with like 90% accuracy. I can't solve those with 90% accuracy myself, right? So it will help. It will raise the bar, which is good. However, I'm not a big fan of CAPTCHAs myself because they happen to be painful for users and they're really not going to slow down the attacker quite that much. Because if the attacker has access to some good algorithms for computing these CAPTCHAs, they can get past it pretty easily.
So is it like nearly like algorithm for solving CAPTCHAs without human intervention, without mechanical job?
Yep, and yeah, I mean, it's an open research area and the algorithms are getting better and better. And yeah, I mean, for most CAPTCHAs, they're much better. Computers are much better at solving them now than humans are. So it's kind of scary. But that's why I'm not a big fan of CAPTCHA approaches myself. But if you wanted to raise the bar, absolutely, it's something you can use. So in conclusion, how did we get here? Right, so we're trying to solve the problem of password storage. However, the mechanism that we choose for storing passwords has side effects. In the case of adaptive hashes, which is sort of the widely accepted approach these days for storing passwords, it can open up your server to denial of service attacks. So how do we protect ourselves? Well, we talked about some approaches that you might be able to combine to protect yourself. Keep in mind that attackers will build custom hardware to still attack you if they're sufficiently motivated. So none of these approaches are necessarily going to be perfect, but it's all about raising the bar. So an attacker with access to just a botnet of 100 IPs can't do anything. They actually have to invest $10,000 and get access to 100,000 IPs before they can do something. Just raising the bar. And if this denial of service prevention seems too difficult, just use keyed salted hashes. That's an alternate approach, but it does introduce that problem of key management that we talked about, and it's not a trivial problem to solve. At the end of the day, though, remember, password storage is only part of the problem. We're really trying to make sure that attackers can't get unauthorized access to our users' accounts. That's what it's really about. Now, according to that same 2007 study by Microsoft that I referenced earlier, 85% of passwords have 40 bits or less of entropy. That makes them all feasible to brute force. Maybe the solution to that is a strong password policy. Maybe we don't allow passwords with low entropy. Users tend to reuse usernames and passwords across multiple sites. It doesn't matter how secure your password storage mechanism is. If your user uses that same username and password on another website and they're storing passwords in the clear and that site's database gets compromised, well, those users' accounts are compromised on your machine, on your server. Well, one possible solution might be additional authentication steps from new IP addresses. So when you get a login request from a different IP that you've never seen before, from a different part of the world, maybe you require some other verification. And many of Google's services, for example, actually do this. So if you try logging in from a different country that you never logged in from before, it might ask you for some kind of a one-time password verification, verifying against your phone number, something like that. Users also tend to fall for phishing attacks. There's some really, really good phishing attacks out there. And there's nothing we can do about that, really, in terms of protecting passwords. Maybe we require some additional authentication steps from new IPs. But good phishing attacks might also be able to get around those and just get the user to provide the information that you would need for the additional authentication steps. Or maybe it's just time for two-factor authentication. It's time to realize that passwords don't really cut it. They've got way too many problems. And we really need one-time passwords or certificates or something else in addition to passwords to authenticate to apps. And that's pretty much all the material I had. Just one quick acknowledgement. Rahil Arora, I actually worked with him over the summer to actually come up with some of the numbers for this talk, and he implemented the SHA-1-based proof of work scheme in JavaScript and allowed me to get some of the performance numbers that I showed you earlier. And that's it. So any questions? Yes, lots of questions. Go ahead.
theoretically at least, drive up the cost of attack by implementing a GPU cluster on our side to do computation.
You could do
I
that.
mean, it costs money, but it costs a lot of money for the attacker too.
Yeah.
Corporation can spend $1,000.
In theory, you could do that. It's just, at that point, it's just a matter of, who can spend more money on it, right? And whatever adaptive hash parameters you're using, they're going to become obsolete probably in another 4 or 5 years. So you have to keep updating that. And also, for a typical enterprise, somebody has to write the software to actually run that GPU cluster and all that. And that implementation, you're not going to just pull some random person's software off a website. You actually are probably going to do the implementation yourself. You could do it, but in theory, yeah, you could do it. Most organizations probably won't.
What I mean is, couldn't that be a possible way in the future that vendors really would have off-the-shelf solutions here?
Yeah, it's definitely a possibility. Good point. Yep.
You talked about limiting the amount of attempts from a given IP. What happens when your primary customer base comes from a lot of people using the same IP, such as universities, things like that?
Yep. So in that case, maybe you have to have certain whitelisted IPs from which you allow greater numbers of login requests. We have to keep in mind, though, that even when all your users are behind the same NAT device, you're not going to get that many concurrent login requests. You might get a lot of concurrent requests, but not a lot of concurrent login requests normally. So we can still just rate limit the login requests and not other ones. And you might have to say, well, for these particular IPs, maybe we allow more login requests and we rely more on some of the other mechanisms that I talked about. Yep.
So I think that we should be very mindful about moving computation on prior side, especially when it comes to browsing.
Yep.
The most painful feature in HTML5 for me personally is non-responsive JavaScript. And it happens everywhere, mobile devices, on desktop, and if you embed this additional load, this problem will be really big. So probably each time when you do that, you really check that user experience.
Exactly, yes.
Second, we thought about mitigating all this problem. I don't like the idea of moving away from this additional salted structure to this key station, because these are all
Yep.
So what if we just, instead of doing what is suggested, just keep your backend safe, make sure that nobody is stealing your salts, right? And if this is how, then running a rainbow attacks will be simply not possible, because your attack space will be huge, right?
So there's two problems with that, right? Number one, everybody thinks that their backend is sufficiently protected and they don't have to worry about it, right? All it's going to take is one vulnerability that even not in your own software, in the underlying layers that you're using, like Heartbleed or something like that, right? And just a bunch of information that you thought was secret now gets exposed to the outside, right? So that's one of the problems. So we can't really rely on just protecting the backend. We have to plan for the fact that at some point our passwords might get compromised. Even,
If you're saying that your backend is not safe, then don't go with your system. In my view, you need to make sure that your backend is protected.
Well, there's.
You can steal all your crashes and all your salts and all of that.
But there's no such thing as 100% security, right? I mean, at the end of the day,
That's right, but like I'm just saying, I said doing that.
you should do that.
Backend has the other requirements and everything, then we'll do such a thing.
Well, yeah, I mean, firewalls will protect against certain types of attacks. They're not going to protect you from app layer attacks, though, right? So if your application happens to have a SQL injection vulnerability, there's no firewall that's going to completely stop it. Yes, web application firewalls will stop some of the easier attacks, but they're not going to stop everything. It's signature-based. It's only going to stop things that are seen before. But at the end of the day, yes, you should do absolutely everything to protect your backend. However, you have to plan for the incident where somebody might be able to get that. Even if, let's say, your app is 100% free of vulnerabilities, what about your database administrator? Is that somebody you completely 100% trust? What if that person just decides that, you know what, I'm going to grab a dump of this database table and I'm going to run with it, I'm going to sell it to someone? Or what about your backup tapes? What if they get lost? Your organization doesn't typically manage backup tapes. I mean, they've get lost sometimes. They fall off trucks. I mean, there's all sorts of things that have happened in the past. You do everything you can, but you can't stop at 100%. And at the end of the day, it's backup tapes. There are many other ways in which it could get stolen. It's just a matter of preparing just in case something like that does happen. Because the last thing you want is to be in the news and somebody saying, well, these guys are using the approach from the 1980s. They're not using the most modern approaches. There's also the issue of image as well. So you want to do everything you can to protect yourself just in case something does happen. And these things do happen. I mean, every organization that's had password hashes stolen, they all thought they were doing a reasonable job. Nobody thinks that we're not going to worry about security, right? They thought they had the infrastructure of security in place. They thought they were doing the right things, but at the end of the day, things happen. Any other questions? If not, thank you very much.